Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Making the Switch to Digital Switchgear. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ABB. ABB is a leading global technology company that pushes the boundaries of technology to enable the transformation of society and industry to achieve a more productive, sustainable future. Innovation has been in its DNA since they were founded more than 130 years ago, and to take advantage of a new technology called electricity. As pioneers in electricity and automation, they help to address the world's energy challenges. Their solutions make homes, offices, factories and transport more energy efficient and safer, and energy more affordable. They envisage a future where the physical and digital worlds merge, making operations safer, more intelligent and more productive. By transforming industries, they are helping to create a more prosperous and sustainable future. For ABB, sustainability is both the right thing to do and a business opportunity. They lead by example by embedding sustainability in everything they do. They champion ethical and humane behaviour to contribute to better lives for people across the globe. Now, today we'll hear from 3 speakers, followed by our live audience Q&A, and I encourage you all to send your questions through to our speakers via the YouTube chat box. I would now like to welcome our moderator for today, Francois I. Francois is Director for Analytics and OT Cybersecurity at Oricon. He has 15 years experience in resources and energy and is passionate about safely unlocking value from mission-critical assets through data and analytics. His previous roles include field engineering, operations management and finance. Please welcome Francois I.
Thank you, Megan, and welcome again to our viewers. I'd now like to welcome our first speaker, Dr. Ian Boak. Dr. Ian Boak is a technical solutions architect with more than 20 years experience in the field of power system studies, operational technologies, industrial control systems, telemetry, teleprotection, intelligent systems, and emerging technologies, and fields including the Internet of Things, Industry 4.0, smart grids, and smart cities. He's adept at gathering requirements, assessing existing solutions, and then developing new architectures to address these within the realm of digitalization of heavy industries. Please welcome Dr. Ian Boak.
Thank you very much for that introduction. So I'd like to share with you 2 perspectives. It's actually 2 things that I'd like to posit with the audience, just about how we as engineers, but also as members of an energy community that consume energy, can participate through the use of digital switchgear to the benefit of the energy transition. So the first challenge that you may or may not be aware of is that of the increasing penetration of distributed energy resources. And there is potentially a way to use digital LV switchgear to maximize that penetration. So it's a scale problem. So just as a bit of a background and a bit of a reminder as to what DER stands for, it's distributed energy resources, and this really represents equipment that's behind the meter. So solar rooftop PV is often understood as DER, but it also includes things such as home batteries, inverters, controllable loads in both homes, at commercial and industrial facilities. Electric vehicles are also deemed as part of DER, as well as smart appliances, things that are connecting to the internet either directly or through some sort of home energy management system. One thing that is often neglected about DER is the knowledge that for this to work, there's a dependency on smart meters, and there's also a need for data services to be provided for this to be orchestrated by aggregators and even for the distribution network service provider or DNSPs to be able to extract the necessary value from this DER. So there's a couple of perspectives I want to also share with you. The Australian Energy Regulator are responsible for awarding the revenue proposals to these DNSPs, and they're always looking for efficiency and prudency in those investments. But they have created the opportunity for energy to be exported from various DERs, aggregated, and then to displace markets generation from centralised coal and gas generation. And they've also recognised that in a future scenario, there's going to be peer-to-peer trading, whereby consumers will be sharing their energy with each other, always in a local network to reduce the losses in the broader network. There's going to be prolific community energy platforms where community batteries are used to soak up excess solar that the grid is not able to absorb. Energy management has been part of the landscape for a long time, and this will continue. The inverters are getting smarter, and the latest edition in AS4777 requires them all to have comms ports, so there's a means to communicate with them. But very importantly, the AR also recognised the need for network visibility. And what is network visibility? Well, it's basically voltages and these power flows that traditionally used to move from one direction towards the load, from the generators to the load, but now actually flows back from households or DER into the network in a reverse direction. So a fairly important aspect that they've picked up on. The Energy Networks Australia, or ENA as they're called, started this journey probably in 2018 with their roadmap, DER roadmap, and they themselves recognise the importance of the grid as the central connection point, almost like an internet connection for power. But there's a need for hosting capacity analysis, and for that, in some instances, to be increased, where the local network doesn't offer sufficient capacity for all of the DER that's been connected to that network to be injected back into the network. Again, they've also identified the need for network visibility, and very, very importantly is to manage the voltage issues, because there's a range specifically within which consumer appliances need to be managed or operated without deleterious damage to that equipment. So they picked up on network visibility as well as managing the voltage issues. Then the third actor in this landscape is the aggregators or virtual power plants. A virtual power plant is just aggregating a lot of DER to mimic the same response as large centralized generators would in terms of providing a wholesale energy, but also probably managing the frequency in the future. They see this as a scale problem, not only in size, but also in terms of the data, because the resolution that they foresee is down to seconds. So just to really emphasize the problem from the DNSP's perspective, there's a couple of issues that they have to consider. The first input is around the forecast. So how many DERs are going to come on at which stage in the future? And then they obviously have to provision zone capacity, zone transformer, which is the bulk supply points, then down to the distribution substations, and then right down to the LV network. So they've invested in what's called advanced distribution management systems to enable that. And that's a system that really has a lot of visibility around the real-time flows of power and voltages, etc., on the medium voltage network, but not so much visibility around the low voltage network. So most of them have a fairly comprehensive network model, and that network model is a geographical information system model, and this allows them to actually see when there's an outage, how many customers are affected, to contact them and to resolve the issue as quickly as possible. Traditionally, there was not that level of visibility down to the LV. Voltage, as I mentioned, is a key parameter to be managed within the network, especially at the end of the network. And in some instances, you don't need complete metering of the whole network. You can use something called state load estimation, which is really a filling in the blanks using Kirchhoff's current and voltage laws to give you the necessary visibility. But it does require a certain minimum amount of metering or measurement on the network. There's always been this issue in terms of capacity of gold plating. And so the prudency and efficiency is very, very important in terms of investing where the problems are and enabling the right amount of DER without curtailment, preferably. So we've mentioned hosting capacity. The network do manage their voltages, but they are pretty limited in terms of tapping up and tapping down the zone transformer in terms of many operations of the tap changer, and usually have fixed taps on the distribution substation. So it is a fairly complex problem from their perspective. It is a problem that scales to the tune of millions of consumers. So if they spend $1 per consumer, that quickly amounts to, say, $1 million in OPEX per year. The problem is also suburb-based, depending on uptake of electric vehicles and solar and batteries, and so that has also shifted their planning. So it's become a bit more probabilistic. It's requiring a lot more information, and it certainly requires a tremendous amount of data. So this is the problem from the DNSP's perspective. So as mentioned, the top diagram just shows that the power used to flow from centralized coal and gas generation towards the consumer through transmission networks, distribution networks, and the distribution transformer or infrastructure, and was then managed in terms of revenue by retailers. The future scenario is batteries, solar, PV, electric vehicles, home energy management systems, standalone power systems, all interacting with each other as well as interacting with the grid. The grid then providing the means for these transactions to take place. So you might think, well, if each consumer had a smart meter, that would resolve the issue. Yes, that is true. And in Victoria, that certainly has been the case as it's been mandated, but that has not been mandated in the rest of Australia. So the consequence of that is that it costs between $10 and $15 per annum per meter for the DNSP to get access to that smart meter data outside of Victoria. And this can quickly add into something in the order of $10-15 million if you had 100% network visibility. So this brought about the advent of network devices, which are put basically at the distribution substation to give an early indicator, a fairly coarse measure of where the problems in terms of voltages, flows, and unbalances are experienced. But at the end of the grid, you still require smart meters to get that visibility. So state load estimation is used with smart meters as well as network devices. So some networks have between 30% smart meters, others are moving towards 40%, and I think the terminal state will probably be about 50% smart meters and therefore data penetration capabilities within probably the next 10 years. Smart inverters, as I mentioned, also communicate the voltage and certain other signals within their networks. So cyber security is obviously a very, very important thing to consider in these future scenarios. So the consumer has a number of overlapping interests. Certainly, decarbonisation is a key aspect for consumers, as well as wanting to be proactive in terms of using their DER, getting greater value out of that, so represented by the top right-hand quadrant. But also there's an aspect of fairness, only paying for services that you use and making sure that the indigent also have a certain level of electricity use. There's a big transition amongst consumers to electrification of transport vis-a-vis electric vehicles, heating, cooling, heat pumps, and most forms of production, in fact, moving towards electricity. There's also a desire amongst that consumers more broadly to promote more use of renewable energy in the network, and this means then potentially also providing energy into that network via community batteries, etc. So this leads to a summary of four potential perspectives from the consumer's view. One is that there's an LV switch, a smart LV switch, that could provide this extra level of communication or visibility on the network, but isn't really seen as part of the solution. Either the smart meter or the network device or even the inverter is seen as part of the solution, but not something called the LV smart switch, which is really a digital device added onto a low voltage circuit breaker or switch. And there's a desire for them to set and forget what they do through high levels of automation and really want very uncomplicated ways of interacting. They're all digital natives by definition, and so very familiar with apps and being able to use those apps to interact with various services. So in terms of an LV switch that's digitalized, it needs to work with an app, and obviously cybersecurity is a key aspect to consider there. So here's a device that I have come across. It's a low voltage device. What's quite important about it is it's at a price point of about 50 cents per ampere, so fairly inexpensive. It has voltage, power flows, current. It even offers a earth leakage or residual current device function. And via a smartphone app, which you see on the left-hand side there, and a password, you can access this device, switch it on through timers, and integrate it with third-party devices. Now, that is typically at no cost to the consumer because it's low volumes of data. And if this data is then made available to DNSPs through some sort of third-party API key, that then provides them zero-cost information right at the fringe of the network. So what does that actually look like in terms of a network? So in bringing this all together, I present to you a single line diagram. At the top of it, it shows the ring main unit, which is the interface device with the medium voltage network, as well as the distribution sub-transformer, and then the aforementioned network monitoring device, which provides a very coarse view of voltage and flows within the network. The DNSP have that network monitoring device, the blue device, under their control, and they monitor that. What the consumer installs are the smart meters, those specifically that get DER at their premises, and that's represented by the little inverter blocks. So you can see on every installation on this particular network, there is a smart meter where there's PV or DER behind the meter. What I'm proposing here is to use these LV smart switches to provide the rest of the visibility, and for that information to be shared via a cloud and a shared API key with the DNSP at no charge, and then that is of benefit to both the consumer for their energy management and controlling their loads, but also for the DNSP to get that visibility in order to provision better hosting capacity, and for the aggregator to orchestrate the best possible value from that DER. So that's the LV perspective that, as engineers and as members of an energy community who use electricity, can use digital switchgear to benefit the energy transition. The next is really the medium voltage perspective. So what I want to talk about is devices out of the automotive industry which have significantly dropped in price. These are devices, microprocessors, very, very powerful microprocessors, and sensors. The sensors are what we call micro electromechanical sensors, fairly low cost but very high precision. And those microprocessors with those sensors put together in devices can be fitted to distribution subs as well as ring main units. Such a system would only cost a couple of $100 and then give great visibility via onboard fast Fourier transforms around acoustic, representing potential arcing, as well as vibration. They measure humidity, temperature, atmospheric pressure, audible noise, explosions, etc., with high fidelity microphones. And this then provides a digitization of all the condition signals of the medium voltage switchgear and even the distribution substation. So if current is added, this can then also form part of that network device at fairly low cost. And this is, something that's retrofitted by OEMs potentially to switchgear and has the longevity and the fidelity of devices used in ABS, energy management systems, etc. Thank you very much.
Thank you, Dr. Ian, for your input. I'd now like to welcome our second speaker, Andrew McDonald. Andrew has been working with NextDC as lead electrical engineer and taking care of the electrical design and assisting maintenance management. Andrew has 25 years experience as an electrical design engineer, mostly for critical facilities including data centers, load flow analysis, fault level calculation, primary and secondary equipment selection, protection relay configuration and coordination, as well as testing and commissioning of protection and communication systems. After graduating in electrical and electronics engineering from the University of Canterbury, New Zealand, Andrew joined Connell Wagner, then Oricon, becoming an associate, where he worked for 15 years as electrical design and site engineer on many projects. Please welcome Andrew McDonald.
Thank you very much for that introduction. Little bit about NextDC and who we are. We are an Australian listed company with recent annual revenue of 246 million. We own and operate data centres throughout Australia. We have 9 facilities located in Sydney, Melbourne, Brisbane, Canberra, Perth, the Sunshine Coast and soon Adelaide. The size of the facilities range from about 2 MVA of load up to facilities currently under design which will approach 500 MVA of load. What we sell is rack space to customers, and the sizes range from sort of quarter of a rack, which is not very much, up to large scale cloud and web service providers which take multiple megawatt tenancies. Data center, basically we hear the term white space, which includes providing very reliable power and cooling to the racks. We claim 100% uptime, and in 10 years of operation, we've never had a service level failure with any of our customers. That means that we've had at least one of the 2 power supplies always on to all of the racks and all of our facilities, and we've always maintained cooling. Our facilities have either uptime Tier 3 or Tier 4 ratings. The Uptime Institute are an international organisation based out of the US that provide reliability performance certification for data centres, and Tier 4 is the highest. Most of our sites are also grid connected as parallel generators. Why digital switchgear? I'll start by introducing what we believe digital switchgear is. Our perception of digital switchgear is that we discard the use of conventional CTs and VTs, and instead we use Rogowski coils for current sensing and capacitive voltage dividers for voltage sensing. It makes extensive use of process and protection buses to, instead of dedicated signals, wiring between the devices, and in our case we're using IEC 61850 with Goose, PTP, SMV and PRP, for those of you who understand what all the acronyms mean. We use IEDs, or protection relays, with merging units embedded or separate merging units to act as inputs to the system, with distributed processing across the IEDs and in other devices. Our requirements for the designs include safety. We want our switchgear to be as safe as possible. It's installed within our buildings and there are people around. Despite the fact we put them in dedicated rooms, we still don't really, it does share the rooms with other equipment, and there are people doing maintenance on some of that other equipment occasionally. We're a data centre, so reliability is extremely important to us. So we want to minimise the downtime of the supplies to our customers. We want to minimise the construction and commissioning time. That gives us a better time to market for new facilities when we build them, and for facility expansion when customers decide that they want additional space or new customers want to move into an existing facility. We want to minimise the area required for our switchgear. The smaller the switchgear, the more racks we can have in other parts of the building, and we get paid for our racks, which makes them far more valuable than switchgear for us. The other advantage is we want real-time control and continuous monitoring of our switchgear, so if we have a fault, we can rectify it quickly. The safety. No current transformers means that there's no chance of leaving a CT open circuit and having the secondary cause arcing, fire and the associated damage and human risk within the switchboard. The Rogowski coils also have RJ45 connectors that mean that the current sensing direction is fixed, so you don't have to worry about the polarity of CTs. No voltage transformers. Means there's no chance of a VT secondary short circuit, which can cause damage and the associated human risk, including explosion of the switchboard. There's no ability for the secondary voltage on the VT to be transformed up to the primary in case work's been happening on the primary side in either bus or line. We don't have to worry about VT star earthing and what configuration it needs to be in to work with a particular protection scheme. And also the RJ45 connection means that the voltage polarity is fixed. The comms bus, instead of secondary cabling, means that there's no chance of a signalling error or a wiring mistake. We've got no secondary cabling almost between our panels, which means that on installation the contractor can't make a wiring mistake with the secondary wiring. We use optic fibre for our bus, which means we don't have copper signalling wiring running between switchgear panels and between rooms. This reduces the risk of spurious voltage transfer across that wiring to somewhere else and the associated OH&S risk that can cause. The sensors are much smaller and lighter than conventional CTs and VTs, which makes the switchgear panels easier to handle, so the manual handling risk for them is reduced. And using optic fibre means the electromagnetic interference risk is reduced and the electromagnetic compatibility is increased. Time minimisation. We have a design, we want to get our facilities up and running as quickly as possible, and our perception is that it would be faster to use the digital switchgear for the following reasons. The only connections we have between our panels are the IEC 61850 communications links on optic fibre, which is pre-terminated, and the two DC supplies for the auxiliary power. All other wiring within the panel is to the IED and done as part of the factory work. It makes for very quick installation on site, as there's not really much wiring for the contractors to link up on site between panels. It also means that any changes on site are typically done in the logic in the IEDs or the other devices, which makes it quicker to make changes to the protection scheme if we have to, rather than having to rewire panels. The logic of the protection scheme is easier to check at shop drawing stage. You receive the logic diagrams in the IED software and you can basically click your way through and check the Boolean logic diagrams rather than having to trace wiring through secondary panels. I certainly found that much faster, and it reduces the time needed for switch shop drawing approvals. The switchgear can also be tested in the factory with the comms bus live, and all of the operating and protection functionality can be witnessed at that point. It means that you potentially can reduce the amount of testing needed on site, which in our case reduces the site installation time. Space savings. The sensors are considerably smaller and lighter than the conventional VTs and CTs. The sensors weigh 400 grams compared with the CTs, which were weighing about 38 kilos in our case, and the voltage sensor weighed about 1.4 kilos compared with sort of 28 kilos for the VTs we were using. They were also much smaller, which means they take up less space in the switchboard, which potentially means you can fit more of them in. The accuracy is better, so the current sensors that we are using are equivalent to a 5,000 amp 0.5 metering class CT with also a class 5P 355 protection CT rating. These replaced 3,200 to 1 15 VA 5P 60 protection CT in our switchboards, which was very large and heavy. Because they are also useful as metering devices, it allowed us to not put metering CTs in all the locations where we potentially would have in the past. The other advantage is that using the 61850 bus meant that the CT and VT, the current and voltage signals can be used in multiple protection and metering schemes across multiple devices and shared over the bus, which reduced the number of current and voltage sensing devices that we needed to install. So the reliability, the smaller sensors and the other advantages allowed us an easier use of a double bus for our medium voltage switchgear. That goes towards our reliability a lot. The unit protection, so we've got differential protection, so that minimised the amount of protection grading that we needed. And the secondary cabling has changed from conventional copper wire with the bootlace and terminal to optic fibre plugs and sockets on a supervised network. So you get a warning if one of the optic fibres comes out, and the network raises an alarm for our facility managers to go and check out. The CT and VT connections are now RJ45, so they're easier to terminate and there's less risk of getting the polarity wrong. No risk, it's fixed. And the communication network over PRP means that there are parallel redundant paths for all of the signalling, which makes our signalling wiring redundant as well, which goes to improve the reliability. We're also using PTP for time synchronization, provides sub-microsecond accuracy for logging and synchronizing the protection. So what worked and what didn't work for us? So factory testing didn't work, primarily due to the COVID pandemic. It was impossible to go to the factory to watch the protection being tested, and it also meant that we couldn't get all of the parts to the factory to do complete testing at the factory. So all our factory acceptance tests were done via video conferencing software, which made it harder. The testing is very different from conventional secondary injection testing, and there's a industry lack of education and a very limited workforce with a limited amount of test equipment that knows how to test the sensors and the IEDs using the 61850 SMV signalling. We got around that somewhat by procuring the testing up front with our switchgear, but that also meant that we had limited vendors willing to tender. The protection and metering requirements of other organisations meant that we still needed additional panels with space for conventional CTs and VTs and some of our medium voltage switchgear. We're a long way away from two organisations being able to link the 61850 buses and share protection information that way, and the national electricity rules require CT and VT for our revenue metering, which meant that we still had to use conventional CTs and VTs for that purpose. Thank you very much.
Thank you, Andrew, for your input. I'd now like to welcome our third speaker, Anisur Rahman. Anisur Rahman joined ABB in 2007, and he's the Digital Systems Center Manager within ABB Australia's Electrification and Distribution Solutions business. In his role, Anisur oversees digitalization and automation products and solutions across multiple segments including transport, mining, and oil and gas. His areas of interest and expertise include smart substation control and protection, ultra-fast earth switching, smart grids, wireless networks, high-speed auto transfer systems, and low-cost load shedding management systems. Please welcome Anisur Rahman.
Good afternoon and welcome once again to the final part of the sessions. In this session, we will discuss the implementation and testing challenges of data center, of digital switchgear. Although this is a case study for data center, but the technologies are applicable for any switchgear digitalization. Let's recap the needs of data center that Andrew already discussed. The prime needs are more safety, more digital, and more reliable. For more safety, he mentioned to use current and voltage sensor. For more digital system, he mentioned to use IC 62850, Goose MMS, and process bus. And for more reliable, he mentioned to use redundancy in all level. Yeah, to easily follow, I divided my presentation into 4 parts. The first of all, the LV switchgear digitalization, then MB switchgear digitalization, then real-time monitoring and control, and finally we will ended up with secondary injection testing. Let's move on. LV switchboards digitalization. The benefit of current sensor already discussed by N2. I will not go through that, but only to few things I want to mention here, that this output of the sensor is millivolt, as he mentioned. So it drive by the di by dt, that means drive by the current. And when it drive by the current, and the all fault current have DC component, and that fixed DC component, part of the DC component, it eliminated when it drives. So that is one of the benefit. And then I will move to this accuracy. As you see in the right side, that accuracy is fixed, and that can be adjusted or corrected by the relay settings. And as you see that the sensor does not saturate, because its characteristics is linear. But the linearity, if you see that, it is up to 50 kA, and that is the main challenges that we faced in LV switchboard. The LV switchboard fault level is more than 72 kA, and the rated current is 500 ampere. So the ratio of all the existing sensors was actually 80:150 millivolt. And if you convert that for 72 kA, the output voltage becomes 135, which is more than the threshold voltage of the REX 640 or any relays. And that's why we need actually to develop a new sensor, and our ABB Czech factory develop a new sensor for LV application with a greater ratio, which is 250:150 millivolt, and it gives us the linearity up to 86 kA. Oh, sorry. Yep. Before I move on to LV and MB switchboard digitalization, I would like to mention this benefit of IC 61850, means how IC 61850 help us for digitalization. As we know that IC 61850 include 3 protocol under one umbrella, means one IC 61850 standard, which are this sample value, then Goose and MMS. And sample value is used in the process level, is in the right side figure. And this actually we need merging unit to convert the analog CT or BT data to digitalize and send it to the relay. And also Goose is a horizontal protocol that used for talking the relay to relay, and MMS is used for relay to SCADA or station level. So these are mainly used for digitalization of any switchgear. Yeah, LB switchboard. LB switchboard have a multiple power sources for actually to ensure the power in the output switchboard. They have the main board, who is take the power from the grid, and along with the in parallel with the RUPS, that rotary UPS, and also the standalone generator source. And at the also there is bus, the IP board is in the ring bus, who is one bus supplied from the other bus, and so on. So yeah, for better protection and control, we use our high end protection and control relays. These relays, REX 640, is all in one protection for any power distribution application. These relays in part of our Reliance series, and it support native IEC 62850 edition 2, means it support GOOS, MMS, and sample value, and also it provides HSR and PRP and PTP redundancy, and finally that merging unit is inbuilt. So we use all this capability to make our LV board and our the LV and MV board digitalized. The main driver to use this relay is mainly the differential protection need two current sensors input, and these relay have the two current sensor input, and we have got a lot of other benefits as well. This relay is modular and flexible design, and for hardware and software, and the software comes in the base functionality, which include all the voltage, current, and frequency protections. In addition to that, it has 13 apps like our mobile apps. So whenever you need, you can download any apps for any protection function, and it is ready to go, something like that. And also it comes with the 7-inch high resolution touch screen HMI, and with only single navigation button. Let's move on. As I mentioned, that the challenges to use current sensor for differential protection, that relay need two sensor input. And there are, see, these MSB, we need actually the transformer differential protection plus REF, restricted outward protection, and we use in this way. And also in generator protection, since the distance is more than 15 meter, we have to use one side conventional CT, and the other side is sensor. And for IP switchboard, for transformer differential, we use both side sensor, and we bring because it is less than 15 meter. For IP bus deep and bus duct deep, this is the bus deep at the top, and the bus duct is we need actually three winding transformer protection, or bus differential protection, and we use sample value here to bring on the two with the sensors, and other is the sample value. Let's move on to medium voltage switchboard digitalization. Here we use our most innovative SSC 600, a brand new way of thinking. It is actually centralized protection and control. You can think this device is one device includes 30 IEDs. So it provides the backup or protection for 30 bays, and as well as the busbar differential protection. The main driver to choose this one is it is simplified low impedance busbar protection. In addition to that, it has other benefit as well. As I mentioned, the modular software is base functionality with current, voltage, and frequency base. And in addition to that, 6 apps it has, whatever protection you need. And it has the time synchronization via IEC 1588 and PTP time synchronization, so that you don't need any additional GPS. Also, it can communicate directly. It can communicate directly to the SCADA or control center by IEC 61850 or IEC 60870-5-104 without any external gateway is in between. So there is no gateway required. So how it works? Mainly, as you know, that it only work with the merging unit. So in all bays, one East Bay, we have one merging unit, and centrally the SSC 600 is here. So merging unit send the CTVT data through sample value IC 659-9-2, and the central control protection and control system SSC 600 provides the protection function, control function, measurement, and centralized monitoring system in the busbar level. So as I mentioned, that we choose these one for SSC 600 for low impedance busbar protection, and it is mainly the simplified busbar protection plus all feeders backup protection. We use REX 640 for main protection here, and it gives the unit protection, differential protection between the MV and the LV. And it provides the backup protection plus busbar protection. So as I mentioned, the simplified busbar protection is actually very simple to configure and to set. And in addition to that, it has integrated check zone, so you don't need any check zone protection, any additional relay for check zone protection. And the through fault detection and open circuit detection algorithm is a complex algorithm to detect that. So you don't need any metro cell or stabilizing resistor to take care. And it has sensitive arc fault protection for the busbar as well. And finally, the dynamic load switching for double busbar. So you don't need any bidirectional or CT switching mechanism. Real-time monitoring and control. So this part we will discuss that how we will provide our ABB ability GE600 Genon energy addition we use for real-time monitoring and control. So this GE600 give us the data acquisition and connectivity, data management and visualization and control, and analytics and reporting. It support actually that up to 300 protocol. So it can be used to integrate medium voltage and high voltage, low voltage switchgear. As you see that it is very scalable. It can be used in a simple, small scale screen to the redundant server, client server orchestration as well. So we used this Genon software in a small scale control system and large scale SCADA in different sectors. This real-time monitoring and control for NextDC, we use these fully redundant systems. Here we use these two redundant systems with HSR loop, and to provide the fully redundant. There is no single point failure to stop the real-time monitoring and control, like in the any loop failure or port failure or any device failure, even switch failure or even panel failure. If one panel goes down, still the other panel can access the whole network. Yeah. Finally, the secondary injection testing. The with sensor secondary injection testing is sometimes people feel challenging, but the for this secondary injection test with sensor, we need the CM leaf that Omicron developed, and thank you, Omicron. And this CM leaf is used as a adapter to convert to provide the millivolt input of the relay. For bus differential protection testing, we had to use this two CM leaf with the CMC 356 with 2LL output, and in addition to that, we had to split the output. And since it is a voltage output, we can easily make the parallel things. This is one of the big benefit of using this sample value. You can split out the output to inject the millivolt. Yeah, this diagram shows that how we tested, and the right side is showing that how we tested different test point to confirm the protection function, the bus differential protection function. Finally, our remote support toolkit, our ST600, is used for remote support. If customer can connect the RST600 box into the switches, and it will give us the communication to our laptop in anywhere, so that our expert can directly support to the site. So we have ABB have all the wireless portfolio, and it is in our digital systems, part of our digital systems. And on that, we using that and the wireless systems, we develop this RST tool, and we are using these for remote support, and this is part of our digital systems. Finally, together we are writing the future. So your knowledge and expertise and experience and our future-proof technology make our customer satisfaction. Thank you very much.